We've been talking about convex lenses, but let's take the case of a concave lens. In reality, there is only one case of a concave lens. We'll figure this out shortly. So again, we've got the focal length, but the important thing here, for a concave lens, the focal length is a negative number. So in this case, the focal length is negative 10 centimeters. Okay, so again, if we're going to draw our three lines, we do parallel. Can't even spell parallel today. Parallel, then through F. 2 is through F, then parallel. And the third line goes through the center. Okay, in reality, when you're drawing a ray diagram for a lens, you only need two lines because they all meet at the same place. Just pick any two lines. But, okay, let's start doing the thing. Normally, I draw my line parallel, and it comes up here and it hits. And I better show what shape lens I've got. So when I show what shape lens I've got, I put in a shape element, and then I go through the focal point. Normally for lenses, this is the positive focal point, this is the negative focal point. So I'm going to go through the opposite focal point than I normally do. So in this case, that means I'm going to put part of my ruler on this focal point, and on where the parallel beam meets the line of action, and it goes up there. So that's actually line 1, and I'll put the dashed lines in just. Okay, so normally we do that. So that's going to be line 1. Make sure they're on the paper. Okay, line 2. So we're going to use the normal focal points. Normal. If we're doing a convex lens, we'd use, for line 1 we'd use that focal point. But because it's concave lens, we use that focal point. And the same here. Drawing line number 2, normally for a convex lens we'd use that focal point. In this case we'd use that focal point. So we use the opposite ones that we'd normally do. So this one goes down through F, or towards F, then it hits the line of action, and then it's going to go parallel. Okay, so this is line 1, this is line 2, and then line 3 just goes straight through the center of the lens. It goes from the tip of the arrow through the center of the lens. Remember, in reality, you only need to be able to choose 2 of these. Okay, so we look at these 3 rays of light, and what can we tell? These are diverging rays of light. These rays of light will never meet. So if they're diverging, what we have to do is backtrack the rays. So I backtrack this ray, and I'm going to put in a stronger backtrack. I backtrack this way, and then, well, if I backtrack this ray, it's going to be through there. So all of these 3 rays meet at this point here. So that's where my image is going to be. Remember, I'm looking from this side. This is where I'm looking from. This is, so, and I see the image over here. So let's do the big 3, upright or inverted. Well, looking at that, it is the right way up, and for a concave lens, the image will always be the correct way up. In fact, most glasses, if you actually wear spectacles like I do, most, for people who are short-sighted, use concave lenses. So it's nice that the image is the right way up. Then we get enlarged or reduced. For a concave lens, the image is always going to be reduced. And unfortunately, if you're short-sighted and you wear glasses, your eyes will always look a little bit smaller because they're reduced. Damn it. Upright, real or virtual. Well, we cannot physically put a piece of paper there and intercept that image. We have to use dashed lines to show where it is. That means it's virtual. And again, for a concave lens, it's always going to be virtual. So, yep, pays your money, takes your choice. Then we basically work out height image and distance image and magnification. Let's see, height image. It's going to be, what's that, about 2 centimeters. Distance image is going to be 2.7 centimeters. And the magnification M equals height image over height object equals 2 over 3 equals 0.667. Okay. Or we can do this the usual way, we can do maths. Let's go up here for a change. Let's go this. F inverse equals DO inverse plus DI inverse. Rearrange that, so we're trying to find DI. DI inverse equals DO inverse minus F inverse. DI equals DO inverse minus F inverse, all to the inverse. So DI is going to equal DO, the object we set up at 4 centimeters, minus 10, but remember 10 is minus 10 itself, and I take the inverse. So basically that's 4 inverse minus is plus 10 inverse equals, take the inverse of that, and that means that the image is going to be 2.85 centimeters, 2.86 centimeters away. I got 2.7, 2.85, so it's actually 2.85. The height of the image, remember, height image over height object equals distance image over distance object. Therefore, the height of the image equals HO times DI over DO equals HO is 3 times DI, which is 2.85. Minus divided by DO, which is 4. Okay, so 3 times 2.85 divided by 4, so 3/4 of that equals 2.134 centimeters. 2.134 centimeters is how tall it is. And what's the magnification? M is HI over HO, which is equal to 2.134 over height of the object is 3 equals, divided by 3 equals 0.7125. So about 0.7. Things to remember about concave lenses: image will always be inverted. It's not inverted, it's upright. Image will always be upright, will always be reduced, it will always be virtual. Brain had a slight mental explosion. Sorry about that. Some people want to say, what about if that's on the other side of the focal point. And that's a fair enough question. What happens if we have a concave lens and, well, before we had the focal length over here and the object here, what happens if we have the object over here? Let's draw a 4 centimeter tall object. And how are we going to do this? And remember, we still do the same thing. We draw the same 3 lines. We saw parallel, then F, to F, then parallel, and finally through the centre. So let's do these rays. So ray 1 goes parallel. Then, because the focal length on a concave lens is negative, we use the opposite focal point that we normally use. So the one on this side, normally we'd use that side. This ray goes physically through there and down. Because it's concave, negative, we're going to use this focal point again. So that's where the first ray goes. The second ray goes to the focal point, but again, normally convex lens would use this one. In this case, we're going to use this side because it's negative. So we draw line down to there, and then it goes parallel. So this is line 1, line 2. And the third line, if you remember, just goes straight through the centre of the lens. We go top of the arrow, straight through. We look at these 3 rays and we go, well, these are diverging. These will never meet. Okay, we call this a diverging lens. So what we do is we backtrack the rays onto this side of the, here we go. We backtrack that ray, we backtrack that ray, the parallel ray, and strangely enough, they all end up at the same point, focal point, the image. So that's going to be the image, there's going to be a distance of the image, it's going to be the height of the image. And then we ask the usual questions, upright, inverted. This one is definitely upright. Yep, upright. We've got enlarged, reduced. For concave lens, the image will always be reduced. And then real or virtual, real or virtual. The thing here is that if I'm trying to put a piece of paper anywhere, I can't put it there. I have to backtrack these lines backtrack the lines, because I have to backtrack them. These are not real rays, therefore it is going to be virtual. And then we can just use F inverse equals DO inverse plus DI inverse, and then M is equal to HI over HO, DI over DO. We can just use that to find out the rest of the data set. And that completes the basic cases of the basic lenses.